Okay. Yeah, Laurentio, I guess, did you want to start first? And
Yeah, so I have some new things, nothing complete yet, but I think pieces of the picture. So let me share this. Okay, so let's see. Okay, so first some basic things of how the boundary for the 2D double moment works. Because it's somewhat similar in other cases where one is discrete and the other is continuous. So here I do X and Y. So it's a double moment in X and Y with both in 0, 1. And in this case, I look at the 2D boundary. And it's given when you have P of X and Y is given to L by L in some disk like this. And then the upper boundary is given when you have basically outside the disk. And of course, you still have X, Y smaller than 1. So then the possible boundaries will look something like this thing here.
sorry, so let me just so you are, so in this case, the 2D space that you're looking at, and you're imagining that the 2D space is for couplings, which are, I mean, because of course it depends on which two couplings, right? You can go like fixed K two couplings or fixed Q two coupling.
Yeah.
So here, I guess you're envisioning the couplings being the diagonal couplings, in the sense that there's an upper and lower boundary. If it's any two other boundary, then it's no longer going to be this, right?
If there's anything else, I think this is still the boundary. I think it's the boundary is given by these two solutions.
So yeah, please.
When you plug the solution into different couplings, then of course it depends what you get, right? So if I'm looking at A00 and A11, for example, with this solution, I get these solutions, and you get some plot like this. And if you were doing some other couplings, then it might look something like something else. But the solution is this.
Okay. Sorry. So what does these two graph mean? Can you?
Yeah. So here I'm showing that basically because you want P to live inside the disk, but you also have this boundary, right? So you also have like X and Y have to be smaller than 1. You have basically two types of boundaries. You have one boundary.
Sorry, can you sorry, what are the axes? Can I understand?
So here, I guess it's X or Y and X. And this, I'm plotting here what the domain of integration is basically. So I'm saying P of X, Y is L inside, say, like a disk here, right? So this is L for like inside the disk of radius R or something.
Okay.
So it's constant everywhere here and equal to the upper bound. And then as you increase this radius, you go like along this boundary like this, right? Up to this point, which is here. And then you have a different type of boundary because now you don't get like a full disk, you get something like this, right? A disk with some pieces chopped off. So then here you get a different kind of boundary. So these two are different functions. Yeah. there's some function 1 and some function 2.
So sorry. So how are you getting these? So these are these again? So sorry. So are these like two-state assumptions, or I mean, what are these?
No, there's no assumption.
So what are the assumption that goes in here? I mean, because you verify these things by numeric plots, right? That's how you're getting these things. I mean, how do you know that these are the optimal? I mean, you're numerically plotting the whole thing, and then you're identifying these boundaries as in this. I mean, identifying what is being plotted numerically by these analytic description of the boundaries.
I compared to numerics, and then if I understood those references, this is what the solutions should look like. So they should be P of X and Y should be constant inside the disk. And then this is for a 2D plot. If you want a 3D plot, then like you said, you don't have a disk, you have like rings where it's just inside here and so on.
Right. But you verified, so you can verify this, you verified this with the explicit numeric plots, right? So in the numeric plots, do you need to assume something like, you don't assume like there's 2 states, 3 states, anything goes, right?
So the way I check it numerically is I try to generate random functions. So because now P of X and Y has to be some function, and I usually, I try to generate some random functions. And of course that's like hard to cover all of the space, but it matches these boundaries okay.
Okay.
Yeah, and it's easy to see that if you pick solutions for your P of X that are things like constant in disks or whatever, that puts you closest to the boundary. So then you know the actual disk is the boundary.
Okay.
Okay. So the important thing here is basically there's this change in functions as once you hit one of these boundaries, right? Because once you go like across here, then this thing is fixed. So there's a different function. Then this will be the same when you have discrete.
Sorry. The domain of validity. Sorry, you're saying that. Sorry, I'm a little bit confused about one thing. So you're saying that there's no. I mean, this upper corner, the upper right corner that is white. I mean, X and Y can go into that corner, right?
No. So I'm assuming here that X and Y are between 1 and 0. So that's.
Yeah, that's assuming, what I'm saying. Yeah, but I'm saying so in principle, X and Y could go to this upper right. I'm calling this upper right that you chop off.
Like here?
Right. No, upper right.
Here.
Yeah.
Yeah. So that's once you go here. So when you fill the whole square, you're at this point.
Oh, okay. So it's not that you chop it, so it can actually go there. Okay, because the way that you plot it seems like you're stopping for some reason at that.
Yeah. So as you go, like increase the radius up to here, you're going along this border.
Okay.
Boundary.
And somehow at that point, the upper bound and lower bound merges.
Yeah. Well, there has to be. The upper boundary is given. So actually, I didn't think too much about the upper boundary because it doesn't matter, but it should be the complement. So I think it's exactly, you fill this region and you go like this, I believe.
So you mean you fill that region, is that you assume that that region is a constant?
Yeah. And then that's the way I think it works.
So why do you say that it's not? I mean, here the upper boundary should be true, right? I mean, in the end, it's gonna carve out this space here, right?
I got it in some way, but I didn't. I wasn't very sure if the boundary is actually like this or if it's still like this. But I think it's. I think it's this thing.
I see. So can you explain? So why is it that okay, but maybe this is because you're doing A11 and A00. If you did something else, it might look different. I just mean that naively, so first of all, for spin bounds, this sounds like I mean, this should be a little bit like truncated, right? Any truncated spin, if we truncate and spin, we can map it into this, right? And then we allow ours to be continuous.
Yeah, it's hard to see exactly how you go from one to the other. So, well, so first of all, if you don't have that x and y have to be smaller than 1, then obviously you just get disks all the way to infinity. So there's just one.
No, what I mean is that the statement that x1 is smaller than 1. I mean, 1 is just some arbitrary number, right? You can always rescale it to be smaller than 1. Right. So sorry, I just mean that if you truncate and spin, you can make it into 0 and 1, right? Is that correct? Or
Oh, if you truncate, well, it's still discrete between.
yeah,
0
forget about the discrete version. So just about the continuous version. If I just think about 0 and 1.
Oh yeah, sure. Then just the rescaling.
Then it's just a rescaling, right? Okay, so this is the first question. The second question is, and then I'm confused about something. So in principle, if we're doing so the discrete version should be tighter than this, right? If we do truncate and discrete, then the discrete bound should be tighter than this, right? Because obvious, right? But then why is it that here? Okay, I just want to know. Yeah, maybe it'll be good to just compare with it just to make sure that the discrete bound is. I just mean that because in the discrete bound, you say that if you take to n infinity, your upper bound is completely irrelevant because it just opens up. But here it looks like the upper bound is always relevant. I guess here the n for you the n equals infinity limit actually corresponds to the 1 goes to infinity limit. Probably is what you're going to say.
It's hard to say. It's not that easy to make a direct connection when you have discrete versus continuous.
But I just mean that discrete should always be tighter than continuous. That's what I'm saying. And if the statement that I think that if the statement that it shouldn't be a problem comparing discrete with continuous, unless we don't know how to take unless we don't, because when we said in another way, as we mentioned today, we need to know what the infinite limit of the discrete, because that's the only bound we have.
Yeah,
right.
But so you can't compare the two, but there's a problem if you want. So this comparison you can do just for even for the single moment. It's you can get an idea. So for the single moment, when you do continuous, let me think. So the problem is for discrete, you need to specify what the allowed elements are. Otherwise, it's this.
Yeah, but like I said, right? I mean, you're just talking about, but the allowed elements, you just mean integer. Is that all you mean, or you mean something more than just integer?
No, that or like any, if you just specify what the terms are, and it's not like anything is allowed, fixed subset. I mean, yeah, even if it's infinite, it's fine. I mean, that's just to define some.
Yeah, sure. So yeah, yeah.
Sorry, there's many confusing things. The problem is if you have and an infinite number of elements, then in principle you don't get any bounds. So the plot, like A1 versus A0, anything here.
Sorry, what do you mean by infinite? I mean, sorry, I don't follow. But what do you mean by infinite number of elements? Are you talking about the discrete version?
So I'm saying that if you have AK defined as the sum going to infinity, some PI X.
Yeah.
Okay.
Yeah. So this is exactly the point that I want to get at, which is precisely is that here in the continuous limit, continuous limit, you're already assuming is infinite, right? You can have infinite number of elements.
Yeah.
Right. So there the upper bound is obviously meaningful, right? Whereas in the discrete version, if you go to infinite, as you say, if you go to infinite limit, the upper bound is meaningless. But at the same time, the discrete version should be a tighter version of the continuous version. So so that's why I'm a little bit confused. But I think that, sorry, can I just say the resolution and let me know if you agree? I think the issue is that if you actually let x and 1 to be not smaller than 1, because if I really consider the whole for the discrete version to compare with the discrete version, where in a discrete version I'm taking the infinite limit, then you're also infinite in spin. So that means that in the continuous limit, there's nothing to truncate, so your 1 has to go to infinity. If your 1 goes to infinity, then you basically just have the lower curve and the upper curve just goes away if 1 goes to infinity. So is that the resolution?
It's not. So that's in the continuous limit. You just get the lower boundary, which is some parabola, and that's it. But now in the discrete, so the discrete is actually not more constrained than continuous, because when you have discrete, you're allowing basically rho of z to be this delta function, right? It's
Well,
like
that's not exactly what we mean by discrete, right? We talked about this many times. It's not really what we mean by discrete. We always mean that there's some small spread and then
yeah,
that's bounded by 2.
I think this is the, I mean, this is what you need to plug in to your continuous thing to get discrete version, right? It has to be a delta function.
Well, it can be, it doesn't have to be a delta function. It can be like a delta function. Well, it can be a small spread. But I mean, this is the old problem about how to get the. But I'm saying that I'm just saying if this is a physics question, right? I mean, what we mean by discrete is the is the like spread out version. It's not really strictly the like isolated. Say otherwise, we're going back to stage 0, which is what do we mean by the bound when we're having discrete. So
yeah, but I think this way it's consistent. I mean, I just think compare continuous with discrete, very like, just, I mean, things should be similar, but I think at the end of the day, discrete, you have to be very careful about this delta function. I don't have like a rigorous way to deal with and to go from point A.
I mean, we can just do the exponential. Like we can do the Gaussian approximation anyway. But yeah, sorry, I'm still confused about one statement. So sorry, you're saying that the okay. Again, I'm slightly worried that the problem is not really the physical problem that we're dealing with. So if you're saying that the continuous version is going to be very different than the discrete version in the sense that yeah, then what is our physical problem? Is it a continuous version or a discrete version? So it's discrete on one side and continuous in the other. So how do we know what exactly, if the two are very different than each other, then how do we, how are we?
Well, that's the problem. Yeah, so that's why I know now how to solve the, like, each equal k equal q, but I'm still having trouble super far away to get like the combined thing. I have some below here, so it becomes more clear. But there's like no mathematical issue with having one discrete and one continuous. It's just the problem of what is the actual boundary.
So actually, but do you know even, sorry, maybe we can go back to this issue again. So yeah, because you're saying that it's very, for you, for the way that you're doing this is going to be very different for you between discrete and continuous. So what is the description? I mean, so okay, maybe I should say it this way. For you, what is discrete? What is the bound that you're imposing on discrete? And for you, what is the bound that you're imposing on continuous? So not the bound on A, but what do you mean by discrete and what do you mean by continuous? So
yeah, so it's basically it's different problems, but the bound is similar. In the continuous case where I have something like this, rho d z k d z, here I impose that rho of z is smaller than L.
where
Like
rho
that,
of P of Z is a smooth function and is a function that is smaller than L everywhere.
yeah, yeah,
Okay.
it doesn't have to be smooth, but it has to be everywhere smaller than L.
So how does that show up in your analysis? The function that you build in is smooth, right? I
Yeah.
mean, so therefore it's smooth. Yeah, okay.
And so, I mean, numerically, you can see that if you have points that violate, then you go outside your regions.
Sorry.
Like,
So what do you mean? Sorry. So what do you mean that by this? So what do you mean by discrete then?
so by discrete, then I mean a Q is usual. So is this, and now PI is smaller than L. So now you have like maybe some finite or some infinite number of states, but it should be some number.
Okay, so we have these two versions of conditions, which in each case you can, okay, and for discrete case, you can get boundaries if the xi are integers, right? If xi's are not integer, then you don't know what you don't really have boundaries anymore, right?
No, I mean, if you know the any xi you give me, you can find the bounds.
Okay.
It's just that it's simplest.
Okay.
Be random numbers.
Okay, so now let's look at our physical problem. So what is our physical problem? So the physical problem is that we have k, and we only have one function, right? We really only have one function.
It's you have different functions for each j basically. Or I mean,
Right.
yeah.
Okay. So if we look at so what version exactly? So what do we do? So yeah. So
yeah. So the only thing I know how to do.
but forget about what we can do. What exactly is the condition on PJZ that we're assuming? So from Simone's point of view, we just have PJZ literally smaller than 2, right? Or yeah, so PJZ is just smaller than 2. So that means that for each J, PJZ is smaller than 2. That's basically the statement. So how do I view this as a discrete problem?
So it's discrete if you look at fixed, right? So on the fixed K column, it's basically a polytope.
Sorry, so how is it? So what is the P in the discrete? So how do you define the rho or the P in discrete version? Because you need to, so your definition of discrete is actually integrating over Z, right? Yeah. So for each J, so can you just write down, so for the discrete problem, what yes, exactly? Yeah.
So let's just do an example. So I'd have A00, the simplest thing, and let's just say I have 2 states for simplicity.
Oh, no, not the solution. I just mean the problem. I mean, just write. Yeah. So it has not. It doesn't have any 2 state in it. It has all J. So I'm not. No, I just want to write the physical problem down. So how do you frame it in terms of the for this? So I guess you're doing it's still AKQ, right?
Yeah.
Yeah, it's still AKQ. So AKQ for a discrete version, you're doing AKQ with fixed K, and you're defining this DZ. So you're just summing over, yeah, but you're defining your rho Z to the K DZ to be your integrate from 0 to 1 to be your spectral function for the discrete version, right?
Yeah.
So can you do that? Can you just write that? I mean, because I just want to know the physical. Yeah. So also because Hudson and Yuan, they can see that. And I think that we should write this explicitly down, just to write the problem down in the draft, in the note, just so that we're all on the same page.
So this is for k, yeah. And then for k equals
Well,
1, then, yeah, and then this integral, you just need, you get the biggest, the largest space where this is maximized. So then this is just 1. Or if it was, if the bound on
sorry.
row was,
Right. Sorry. So what is the condition on your PJ?
so on PJ, now it becomes, so if I had, sorry, let me find some more space somewhere.
Yeah, do you have a paper that you can regularly write on? So can we just write on a piece of paper or a blank? Yeah, that'll be helpful. Yeah, that'll be far better.
Okay, so I had a,
Actually, you don't have to. We can just write AKQ, right? We just do general AKQ. Aren't we? We don't have to do it like one at a time, and we're defining the physical problem, right? Right. So if you want to consider fixed K and then various Q where the Q, and you want to consider this discrete problem, you will write this problem as,
so just right here, then let's just do 1.
okay. Sorry,
Now basically,
you're missing a ZK.
yeah.
So you're just gonna you're calling that PJ, right?
Yeah.
And PJ is bounded by integral from 0 to 1 ZK dz, right? That is what it's bounded by.
Bounded by where this is maximum, right? So the maximum is 0, 1. This is L, or sorry, is the 1.
Yeah, this is 1. Yeah, ZK dk dz.
Which is 1 over k plus 1.
Right. So this is a discrete version of the bound. Right. And then
So
what?
No, sorry, that's it. Yeah. So basically now you get a k is basically sum of.
Sorry. So this is, yeah. So okay. Yeah. You continue. Sorry.
Yeah. So now it's PJJQ, right? Over J, where now PJ is bounded by 1 over k plus 1.
Yes. For AK, right. And for the continuous version, how do you do this? So if I'm looking at the continuous, sorry,
Yeah, you do.
Meaning that I'm looking at the 0 to 1 part. So that's the problematic part, right?
Right. So then you do it just basically the other way around. You do
Yeah. So
0, 1. You do the sum inside here. It's going to be rho J Z J Q C. So now basically I define this thing as my rho JZ. And now this will be smaller than.
sorry, you define it. Sorry, you define that as your rho Z, right? There's no longer J in. You already sum over J. You already sum over J.
Right.
Right.
So then you define this new thing as just basically it's going to be smaller than the sum over JQ, again, where this rho J of Z is maximized, so 1. So it's smaller than this.
So this
now
is
I get
divergent, right?
Yeah. If you go to infinite, n is divergent. So then.
So I guess that means that in the AKQ in this direction, I mean, it's the original bound, right? Meaning it's not projective.
Yeah, it's not projective.
Sorry, it's back to projective. Sorry, it's not deprojected. Sorry, it's because it's just rho J is positive.
No, but it's smaller than this. It's smaller than some.
No,
the point here.
But the point is that we're supposed to let J go to infinity, right? Unless there's some reason that J is, yeah.
Yeah, so I think I don't know all the way how it works, but my suspicion is you'll need to have some finite n all the way up to the end and take the limit after you do all of the null plane and all of that stuff. That's how I think it will apply.
But I mean, just constraint wise, there's no reason why yeah, I mean, yeah, okay, but at least at the mathematical front, the point of here, it looks like if we fix this, I mean, in this way, things are going, I mean, this is just unprojected, right? Rho Z is just, the only thing you can say about Rho Z is it's bigger than 0.
Yeah. Yeah. It might be enough. It's hard. Yeah, it's hard to say exactly because actually to know how the null.
I mean, strictly speaking, because here when you're doing this, you're just talking about the fixed Q constraint, right?
Yeah.
So, and we know that the fixed Q constraint doesn't really talk to the null plane much unless you combine a bunch of other things, right?
Yeah, it's only it
right,
helps you go down in like lower.
Yeah, so the fact that the fixed Q constraint in this, I mean, in this rigorous way of doing things. By the way, yeah, in this, so for our, yeah, this rigorous way of doing things is going to be unbounded. That's expected.
Yeah, well, so one thing is this. For the moment, I would say for certainty, this way of doing things is valid when you do a 2D plot. When you want a 3D plot.
Sorry, we haven't said about, okay, maybe I'll let you finish. Because I mean, this is just setting up the problem. This is not any way, right? We're not saying it, yeah, we're not dealing with what exactly is the constraint. We're just saying what is actually coming from physics, from the equations. From the equations, J goes to infinity, and this is just unbounded.
Yeah, well, yeah, I'm not sure what happens if you have, so you can justify this when you have just do a 2D plot, because then you know what the boundaries are, so then you can just check that this is consistent.
Sorry, I mean, we're talking about, I mean, I thought that, sorry, I don't know what you mean. I mean, yeah, I just mean that even the problem, when you're doing it like when you talk about 2D plots, you're solving a problem, right? You're solving you're talking about, you know, the boundary of a particular problem. Here, we're just talking about the problem itself, not solving it. And I'm just saying the problem itself is unbounded. So it's not about solving. So that's why I want to make things clear what is actually coming from physics and what is, I mean, for various different mathematical scenarios, we have different solutions, but what exactly is from physics? And so I think that here what it says is that from physics, the fixed Q order is unbounded. If we're doing the fixed, yeah, so it's not always bounded. So it's really only bounded in the, I think from here it's clear, it's really only bounded in the fixed row. If you just talk about fixed column, is unbounded in the fixed column. I mean, I'm just talking about the problem itself, the nature of the problem.
Yeah, it might be consistent still. Yeah, okay. I was kind of worried that because it's unbounded, you don't get anything. But of course, we know you do get something even when it's unbounded, but just not in like a 2D plot, right? When you're doing the old story where the p's are not bounded, if you try to plot anything like A0 versus A1, there's always just a trivial, there's no boundary, right? It's only when you go to a 3D plot and maybe do projective, then you get some finite region. So here maybe it's just the same. It's just the same as unbounded in the continuous moment curve, but just, yeah, so maybe it's fine to just
yeah. So I'm talking about, yeah, so if we, right, so so I'm saying that if we so of course, as always, when we first attack the double moment problem, we look at the fixed column and the fixed row. So it looks like the fixed row is a new bounded problem, but the fixed column is not a bounded problem. So that's probably the nature of the thing that we have now. So either we, so if we, so of course it'll be great to already, if we have, so the first, so it sounds like strategic wise, we go to the fix, the fix, and then this for the fix row, and then we have these bounds associated with the discrete problem that Laurentio has, and then yeah, and then we need to, and then of course first is once we have these bounds, we can recycle these bounds, and then feed it back to the original machine and see how everything plays out, in the sense that, but then I guess what Laurentio wants is you really want to have the double moment issue. But that's what I'm saying. The double moment issue, then we need to talk about, we need to move, if we want to move beyond the double, then what exactly is the problem? So I want to be really precise about what exactly is the problem that we have. So I think the problem that we have, yeah, so it sounds like, yeah, okay. Okay, the problem, strictly speaking, is that we just have rho JZ where rho JZ is smaller than 1. And that's it, right? It's a continuous function of Z, and it carries a discrete label of J. So yeah, so that's the, okay. Did you want to show us something more?
Yeah, so just to get an idea, so here I'm doing A00 versus A11, so it's like the first actual double moment.
But for this, you really have 2 continuous labels, right?
No,
So
here it's one is spin and one is mass.
Sorry?
So here AKQ is one, this is like sum and integral.
Oh, so this is a physical problem.
Yeah, close to it, without some extra factors. Yeah.
But so what is the condition on rho J? So is it literally just rho JZ is smaller than 1? That's the only thing you can put here?
Yeah, and so you can find the boundaries. Again, for a 2D plot, it's easy to find the boundary.
Uh-huh.
So I can go over that, but it's not so important. I mean, basically, you have different, say, like row 1 of Z, row 2 of Z, and then the boundary is given by, this is a step function up to some value M, and then one boundary is this will be, if you have this for spin 1, this is for spin 2. One boundary is, this is like M, and then the next one is M over 2, and then the third one is M over 3, and so on.
Sorry, what is the condition on row? Okay, so in each, okay, sorry, never mind. So each row 1 Z is always just bounded by the same number. So rho JZ is bounded by the same number. Okay.
Right, so this is one boundary, and then anyway, you can figure out what all of these 2 boundaries are, but you can solve analytically. And then here I plot the conditions that you get on the equal K and equal Q. So you can do like 0, 1, 0, 0, 0, 1.
And then you project down to 0, 0, and 1, 1.
Here you have the fixed Q, and then like this, you have the polytope and so on. So you impose all of these conditions like this. And you see it's quite close to the actual thing. And what's missing is obviously something that combines all of these things.
I see. Sorry, so Lorenzo, so here when you say that exact boundary 1 and 2, here, okay, so first you assume that the boundaries configurations are like this, and then you just solve it, right? That's basically how you get the boundary. And then you do numerical to verify that these are the boundaries.
Yeah.
So when you do, so 2 things. First, when you do numerical, do you actually see that the, okay, so they're always inside the boundary. Okay, I guess then what do? You just you just do some rho z, you just assume some rho z functions for some rho j z function? Whereas,
Yeah, so
yeah.
yeah, it's easy to convince yourself that the boundaries always are a step function.
Uh-huh.
The only variable is like the length of the step function in 2D. And again, if you're in 2D, then you have more of these. But in 2D, you have just one parameter for each row of Z.
Mm-hmm.
And then once you know this, then it's easy to figure out what the pattern is for the boundaries.
I see, cool.
And yeah, in general, it's easy to figure out. It's something like this. Again, you have two boundaries. So the first boundary when you're going, say like this, it's basically you have this line that you're pushing up and you have the first row goes up to here. The second one is half just because the next spin is half. And then you keep going up, you're going up here, you're going up here like this. And then once this thing hits 1, so because Z is bounded by 1, then the remaining boundaries given by this is always fixed number, and then it's just the others have 3 parameters and so on. So, and then you can do it in general, and you see you have like a bunch of different boundaries.
Oh, that's cool. Sorry, so this is okay. So you actually have I mean, forget about the double continuous bounded from 0 to 1. Basically, you have the answer.
I know the boundary, and yeah, but
sorry, so in here when you have multiple spins, you have 2 states. I mean, are you assuming which 2 states these are, or what is the?
yeah. So I'm usually starting with spin 1 and then 2, and then as I increase n, I just add the next thing. But it's not hard to just do any random numbers you want.
Sorry, so
just spin.
Yeah. Sorry, but for when you choose different, the boundaries are slightly different, right?
Yeah, for the polytope, it's not a problem because it's just consistent, and it just depends how high you need to go. Like right for the null plane, then as long as you hit the null plane, then you don't care what happens higher. For this thing where you have
yeah, but right now, sorry, I'm a little bit worried about how. I mean, yeah, I mean, presumably the null plane looks like that, but we want to be precise, right? Because this is not really our original J. This is really L now. So it's slightly. I mean,
yeah.
to get back to the original thing, you need to go through a bunch of projections. So yeah.
Yeah, in that case, you don't need to project anything. It's just you're instead of giving me spin like L equals 1, 2, 3, and I make the polytope, you're basically giving me just 2L plus 1 L plus L. So you're giving me these numbers. But once you give me these numbers, I can just do the polytope. Just plug in xi is equal to this thing instead of I. Just the polytope is concerned.
You mean the sorry, I'm not following. Are you're just saying that because the boundaries of your discrete version is actually always written in terms of stuff like 2L plus 1 and plot and stuff. It's always going to be is that why, or what is it? I didn't follow.
I mean, the polytope just depends on what you have this, and then you have xi q, and then if you give me the xi, then I know what the polytope is. So it doesn't matter what the xi is. It could be like xi could be 1 over I squared. You still get some polytope. Or it could be this, right, in terms of spin. So the boundary of the polytope, is just like 1, A0, A1, 1, and then here it's exactly just sum over xi, and then sum xi squared. So if you know all of the xi, then you know all of the boundaries.
So okay, so sorry, doesn't this sound like you're saying that you basically have everything you need?
No, because I basically only have, so I know how to write the constraints for equal k and equal q. At least in 2 dimensions, I checked that everything is consistent. And then in general, I know how to get the boundaries, but I don't know what the conditions are. So in the sense that I know how to get the parametric plot of the boundary. And from then I can work out the constraints on the couplings, but I don't have a direct way to get the coupling space for the double moment.
Sorry, what is, sorry, first of, okay, once again, so first of all, for the row and the column, everything is done because that sounds like, I mean, for one we have unbounded, the other one we have bounded, and the bounded is actually the 0 to 1 bounds, and that's very clear. We know we will even have the exponential map for that bound when it's bounded by 0 to 1. But and so for the, but then for the double moment, problem, here you're formulating the boundary. So here you're just looking at the example in A00 and an A11 space, and you're postulating that the boundaries that you found takes those particular form. But I guess so the question is, okay, I see. These are the question is okay, we still don't have an understanding for what is the full boundary, in the sense that even how do we even organize the couplings to look at the boundaries, right? So previously we know so previously we know that we want to organize in terms of general Hankel matrix and look at the determinants of Hankel matrix or the minors of the general Hankel matrix to determine the boundaries. So I guess here the question is that for the double moment, we don't even know how to organize the coupling to. You're basically going on a case-by-case basis just to explore the possibilities. Yeah, I think. Yeah, okay. I think that, sorry, Hudson, do you have a question?
No, I was just burping.
Okay, so I think that, okay, I think that at this point, probably we should, Hudson, okay, the recording, I think we should really do like a brainstorm session thing about how to, I mean, Lorenzo has done, yeah, you already have these great examples. So, but I feel like now is the bottleneck where we really need to think about. Of course, we can already do analysis, right, just to see what these bounds actually give us. But as at least it sounds promising that the 2-dimension bound, where when you compare to the column and the row bound, is actually already pretty close. So even if we just land on the column and the row bound, but maybe we should, yeah. But the question is, how do we organize these things in a more systematic way? But okay, so I think we should probably really do a roast. Unfortunately, I don't think that you guys really want to like get together and sit in a room on a blackboard. So I think that we should probably set up a time to really discuss these issues. So it'll be good for, so I'll put a message in our messenger. So it'll be good if we can actually, yes, for other people to just get on the same page of where we are now, and then we have a discussion. So yeah, so okay. Before we set a time, so Hudson, do you want to discuss something?
Okay, let me share my screen. Okay, so do you see my screen?
Yes.
So okay, this graph is the graph you saw last time, and there is only a Q exchange considered, and now I have the full crossing symmetry, including ST exchange. So we will have this graph. So plotting them together. So this is the
Oh, so
the
this
space.
is
Yeah.
I see. So this is
So this is the space.
right. So sorry. So the original plot will be the same plot as in Zvi's paper, right?
Yeah, yeah. And the old EFT from paper. This is this plot.
Cool.
And if we include the ST symmetry, we will get this red one.
Sorry, but I thought that they also what do you mean by ST symmetry? So sorry.
Sorry. I mean, if we consider this minus plus plus minus and impose a no so if we exchange 1 and 3,
I see.
MB will get MC.
I see. So you're saying that you include the constraint coming from the okay. Right.
So we will get this red region.
Sorry, can I ask? Sorry, you're talking about you're looking at the. So Zvi was looking at plus plus minus minus, right?
Right, right.
You're saying that you're including the constraints coming from plus 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 and minus 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 minus.
Oh no. Plus. Sorry. Minus plus plus minus.
Oh, so this is something new. So there's no positivity from that condition. But you're saying that because the couplings, and that's, I mean, there's no positivity because you have this -1 to the L, right?
Yeah, yeah.
But you're saying that just from the
yeah, the 3-point couplings are the same.
right. So just from the 3-point couplings themselves, they're actually imposed constraint. Oh, this is interesting to see. Okay. I guess now what you want to do is you want to impose higher K, right? To run
Yeah, this is only K equals 4 constraints.
Cool.
Okay. And I checked a little bit about the amplitude is a bracket times this amplitude, or this is a full scalar and the STU. And we will get these two amplitude will give us the same point. That's this coordinate is 2 and this coordinate is 3. So it does not span the space. It's just 1 point in that region.
Sorry, but if you do linear combination, okay.
Yeah, I did linear combination here.
I see.
So it's the same point.
Huh. That's weird. How is it the same point?
Well, if you calculate this one, this will give you 2 and 3, and if you calculate STU, it will also give us 2 and 3.
Sorry, but doesn't this sound a little bit weird? Let me think. Because
maybe because it's the same. We are considering OK equals 4, so the mass dependent.
I mean, no, I just mean that.
Well,
sorry.
there's just one coupling, right?
Oh, sorry. This is 4-1 and 4-2. This is not the same couplings as in with the STU in the scalar amplitude, right? The scalar amplitude is it 4-0 and 3-1? What was?
Yeah. 4-0 and 3-1.
But this is slightly different. No, I just mean that, you see what I'm saying? I'm just saying that this you could have done this for the scalars, right? I mean, this is the scalar amplitude, right?
Right.
So are you saying that? Sorry. So are you saying that actually forget about this the spinner? I mean the spinner bracket. If you're looking at this, you're saying you're actually saying that these two amplitude don't actually span the whole state, even for the scalar EFT hedron, right?
Scalar.
Right. That's what you're saying.
Oh, right. Yeah. Even in the
we should understand this. Are you or do you is any one of you trying to do the plotting other dihedron plots and just see if these two span those spaces?
I haven't do that, but I can use it by SDPP.
Yeah, so this will be, we should really understand, because this sounds like you're saying something now. This is now interesting, because you're saying that it'll be good to just verify this, because I mean, so it looks like that for 3,1 and 4,0, these two amplitudes span the space, but somehow for 4,1 and 4,2 it doesn't span anymore. So now it depends on which couplings. But I'm a little bit surprised, but it seems like this is what you're telling me, that it depends on the coupling. Oh, yeah, it depends on the coupling. Right? That's what you're saying. Of course, that was normalized by 2,0 and you're normalizing by 4,0, but that makes no difference.
Right.
Yeah, I'm still a little bit surprised by this. Is 4,1 related to, I'm a little bit surprised. So you're saying that A completely drops out?
Yeah.
That's weird. Why is if A completely drops out, doesn't this say something? Sorry, so what if you do 3,1,2,0? I mean, just do, is it always
but we now have to multiply the mass gap right now.
No. I mean, these two amplitudes are not the same amplitude. I mean, we're just.
Oh yeah.
This has nothing to do with.
Yeah, so it doesn't.
Oh, so here you have A dependence, but that's interesting. So is it because you're what if you do 4,1 and what if you do 4,1?
Oh, sorry.
Yeah. Well, what if is it because you have what if you do 4,1 and 4,0? Yeah. Now let's do it again. Yeah. So I think it's just because you're normalizing it by 4,0. Right. If you normalize everything by 2,0, you have the A dependence back.
Yeah.
So I think that's the so I guess the A dependence at fixed K is always it probably has some universal behavior for the A dependence at fixed K, and therefore if you divide things at fixed K, it'll always drop out. Yeah, I think that's what's going on. Okay, so you can see if it spans the region.
Yeah.
Okay, cool. Okay, so what times do you guys think will be good? Will Friday be good?
Yeah.
No, Friday is not good for me.
So what about Thursday? What about Thursday evening?
Okay. Yeah, okay. Thursday evening.
Okay, so okay, let me just send a message and we'll see time Thursday will be good.
Okay.
All right, okay. Thanks, guys.
Thanks.
All right, bye.
Bye.